Okay, welcome back to the deep dive. We're diving into something today that might sound like it belongs squarely in the realm of science fiction, but it's actually the focus of intense research and planning happening right now all around the world.
That's absolutely right. While 5G is still rolling out, and frankly, we're only just starting to see its potential unlocked in certain areas, the next big thing for mobile connectivity is already being mapped out. Researchers are looking very seriously at what comes next, and that's 6G.
Exactly. And to really understand this next leap, we've been, well, digging into a whole stack of source documents, as the early visions, the conceptual papers, the roadmaps being sketched out for the sixth generation of mobile networks. So our mission here is to unpack these sources for you, try to get past the technical jargon and maybe some of the hype, and really get to grips with the fundamental ideas and, well, the pretty ambitious goals behind 6G. It really seems like it's about more than just a faster phone connection.
Oh, much more. We're talking about a conceptual shift, really. One that could fundamentally redefine the relationship between our digital lives, the physical world around us.
That sounds big. So, okay, first question then. If it's not just about faster downloads, what's the core vision? How is 6G actually conceptualized as being different from just, a supercharged 5G?
That's really the crucial starting point in these documents.
Yeah.
The vision for 6G, it isn't pitched as just an incremental upgrade. Like if you just slap more speed onto 5G, you kind of miss the point, the revolutionary aspect.
Okay.
The way these sources frame it is more like a progression. So 4G was mostly about connecting people, right? Mobile internet, apps. Then 5G started seriously connecting things, the Internet things, sensors, smart factories, that kind of thing.
Right, the IoT focus.
Exactly. So the leap to 6G, the core idea is about connecting intelligence.
Connecting intelligence. Okay, what does that actually mean in practice?
Well, it means the goal isn't just moving data bits faster. It's about creating this seamless, pervasive digital fabric, one that isn't just passive, but is actively sensing, processing, and even interacting with the physical environment in, like, real time. It's envisioned more as a distributed platform. Intelligence isn't just in the cloud or on your device. It's sort of embedded throughout the network itself. And this fundamentally starts to blur the lines, between the digital representation of things and the actual physical world. Maybe even some sources suggest our biological world eventually.
Wow. So the network itself stops being just the pipes, the infrastructure, and becomes an active, intelligent participant, almost like it's aware.
That's a really good way to put it, yeah. It's about synchronizing digital models with physical reality to a degree that's, well, hard to fully grasp right now. Enabling applications that need that kind of deep integration, that awareness and responsiveness.
Okay, I think I'm starting to see how this is more than just speed. But while it's more than speed, the performance goals mentioned in these sources, they are still pretty mind-blowing, aren't they? What kind of numbers are we talking about?
Oh, they are definitely pushing the absolute boundaries of what seems technically possible today. To support this vision pervasive intelligence, this fusion of digital and physical, the performance targets have to be extreme.
Right.
So they're looking seriously at using ultra-high frequency bands, specifically the terahertz spectrum, which is way, way higher than anything used in current mobile networks.
Terahertz, that's getting up there frequency-wise.
Very high frequency. And the reason is these bands open up absolutely vast, unused stretches of bandwidth, continuous chunks of spectrum.
Which you need for massive speed boosts.
Exactly. So the goals being discussed are, well, speeds significantly over 100 gigabits per second as a baseline, but really pushing towards peak data rates in the terabits per second range. That's 1,000 gigabits per second.
A terabit per second.
Oh.
That's difficult to even imagine. What would you even do with that instantly?
Well, imagine downloading, enormous data sets, entire virtual worlds, complex models in literally the blink of an eye. Things that currently take minutes, hours, maybe even days.
Okay, that's the speed side. But speed isn't everything, especially for the kind of real-time interaction you mentioned, right? Latency, the delay, that's got to be just as critical.
Absolutely critical. Maybe even more so for some of these envisioned applications.
Yep.
And this is another area where 6G aims for a truly revolutionary jump. The target is to slash latency down to the microsecond level.
Microseconds, not milliseconds like we talk about with 5G.
No microseconds. We're talking near instantaneous communication, essentially aiming for zero perceptible lag. The idea is to remove any delay that could possibly hinder, real-time remote control or high-fidelity sensing, or those truly immersive, believable virtual experiences.
Microsecond latency.
Yeah, that's the kind of responsiveness you'd need if you were, say, performing remote surgery with robotic arms or trying to make a virtual world feel completely real and interactive.
Precisely. It's about enabling interactions that feel truly instantaneous, allowing for perfect synchronization, whether it's between the digital and physical, or between multiple robots, or even between humans and machines in a very direct way.
This idea of the network itself being intelligent, it keeps popping up. The documents mention pervasive intelligence and AI native network. So how is the role of AI in 6G actually different from how we use AI in, say, 5G networks today?
Yeah, this is a really fundamental architectural shift they're talking about compared to 5G. You see, in current networks, 5G included, AI is often used more as, well, as an application or a tool that runs on the network.
Right, like using AI for optimizing traffic flow or maybe spotting security threats, things managed by humans running AI tools. Exactly. AI running on the network. The 6G vision, though, is for AI to be deeply woven into the very fabric of the network itself. It's not just managed by AI. The network is an AI system in a distributed sense.
Okay, the network is an AI system. What does that look like? What kind of operations would AI be controlling?
Well, think about managing those incredibly complex and frankly quite fragile terahertz radio waves we just talked about. An AI-powered air interface could intelligently shape and direct those signals in real time, adapting constantly to the environment, the user's movement, potential blockages. Then you've got AI-driven control planes managing, well, everything else: spectrum allocation, power consumption optimization, data routing, predicting network congestion before it happens, and rerouting, even self-healing from faults or failures. All done autonomously with minimal or perhaps eventually, no, direct human intervention needed moment to moment.
It really does sound like the network evolves from just being passive infrastructure into this complex, self-managing, almost like a living digital entity.
That's a pretty good analogy, actually. And that level of intelligence is seen as essential. I mean, how else could you possibly handle the sheer complexity, the scale, potentially trillions of connected devices, and the incredibly dynamic nature of a 6G system operating at those extreme frequencies and speeds?
Okay, that makes sense. Now, speaking of the network interacting with the environment, the sources introduce this concept that sounds genuinely new, maybe even a bit startling: sensing as a service. What on earth is that?
Right. This is definitely one of the more revolutionary ideas floating around in the 6G discussion. It basically leverages the fact that a wireless network, by its very nature, is constantly sending out and listening for radio waves. That's how it communicates.
Okay, standard communication. So what's the twist?
The twist is using those same radio signals, not just for communication, but also as a kind of pervasive radar or sonar system to actively sense the physical environment all around the network infrastructure.
Wait, so the network hardware itself, the base stations, the access points, could use the radio wave to see or sense what's physically around them?
Essentially, yes. By analyzing how those radio signals bounce off objects, how they're reflected, absorbed, scattered, the network itself could potentially gather detailed, real-time data about its surroundings.
Like what kind of data?
Things like detecting objects, tracking their movement and speed, measuring distances, maybe even creating real-time 3D maps of the immediate physical space. Some concepts even suggest gathering environmental data like temperature, humidity, air quality, just by how the signals propagate.
And the key is this would be done using the communication signals themselves, without needing to deploy billions of extra dedicated sensors everywhere.
That's the vision, yes. The communication network becomes simultaneously a vast, distributed sensing network. It provides this intrinsic, real-time contextual awareness of the physical world.
That's wow. The implications are huge. Smart cities that truly understand pedestrian flow and traffic patterns without extra cameras. Buildings that know exactly where occupants are for efficiency and safety.
Exactly. It provides this fundamental layer of real-time physical context that the network's own intelligence can then use, maybe to optimize the communication links themselves, or manage resources more effectively, or feed data into countless other applications that need that physical world awareness.
Okay, with capabilities like pervasive sensing, connecting intelligence, maybe even brain-computer interfaces down the line, security and privacy just become exponentially more critical, don't they? And scaling all this up, the power consumption must be a huge concern. How are security and sustainability being addressed in this 6G vision?
You've hit on two absolutely crucial points there, and the sources are very clear. These are framed as paramount design constraints right from the outset. They're not features you bolt on later. They have to be baked in from day one.
So, starting with security and privacy.
Given the potential sensitivity of the data, real-time location, environmental sensing, maybe biometric, or even neural data, eventually the goal is to build even more robust, fundamentally secure mechanisms deep into the network's core architecture.
More robust than 5G?
Significantly so is the ambition. The sources even talk about exploring potential synergies with principles from quantum communication, things like quantum key distribution or QKD, to establish provably secure communication channels that would be resistant to future threats, including attacks from powerful quantum computers. Trust, resilience, privacy protection, these are seen as non-negotiable pillars.
Okay, quantum level security built in. What about sustainability? All the speed, all these devices, pervasive sensing, AI running everywhere. It sounds like an energy nightmare.
It absolutely could be, and that's why extreme energy efficiency is highlighted as maybe the critical requirement alongside performance. The vision demands this enormous leap in capability, terabit speeds, trillions of devices, sensing AI everywhere, but it has to be achieved while drastically reducing the energy consumed per bit transmitted or per computation performed compared to 5G and previous generations.
So doing vastly more with vastly less energy per operation?
Exactly. Powering potentially trillions of future devices, many of which might be tiny, low-power sensors, plus the immense data processing distributed throughout the network. It simply has to be sustainable. Otherwise, the environmental cost would be unacceptable.
That sounds like a monumental challenge in itself, building systems that are simultaneously incredibly powerful and incredibly frugal with energy.
It is. It requires fundamental breakthroughs across the board. Materials science for new low-power chips, innovative antenna designs, ultra-efficient network protocols, lean AI algorithms specifically designed for energy optimization at every single layer of the system.
Okay, so making this whole vision a reality clearly requires pushing the absolute boundaries of current technology. Let's talk more about some of that cutting-edge tech researchers are exploring. We keep mentioning terahertz frequencies. Can you unpack the significance of T-hertz a bit more and what the really big challenges are there?
Right, terahertz or T-hertz. We're talking about the frequency range roughly between 100 gigahertz and 10 terahertz. It sits between microwaves and infrared light on the spectrum. The key significance, the reason researchers are so interested, is the sheer amount of unused bandwidth available up there.
Just empty space on the radio dial, essentially.
Pretty much, yeah. Vast, contiguous blocks of spectrum measured in the tens or even hundreds of gigahertz wide. Compare that to the relatively narrow channels we use for 4G and 5G today. This is the only place left in the radio spectrum where you can find enough raw bandwidth to realistically achieve those multi-gigabit, potentially terabit per second data rates.
Okay, so it's where the highway for massive speed exists. What's the catch? What's the big but?
Well, the catch is pretty significant. Terahertz signals are notoriously difficult to work with using current technologies. Their primary drawback is extremely high propagation loss and short range. We're talking maybe just a few meters indoors under ideal conditions.
A few meters.
Yeah. And critically, these signals are very easily blocked or absorbed by almost any physical object. Walls, furniture, people walking by, even atmospheric conditions like dense fog, heavy rain, or even just the moisture in the air can severely attenuate them.
So you've got this incredibly fast signal that struggles to go through a window pane or travel across a room if someone walks in between. That sounds like a massive hurdle for building a practical, ubiquitous network.
It is, absolutely. It's probably the single biggest physical layer challenge for 6G. It means the traditional model of putting up a few large cell towers to cover a wide area just won't work for T-hertz.
So what does work?
It demands entirely new approaches. Things like extremely dense deployments of very small, low-power access points or antennas, maybe integrated into ceilings, walls, street furniture, and it requires fundamental breakthroughs in semiconductor technology, new materials, new chip designs that can generate, process, and detect these ultra-high frequency signals efficiently and affordably.
Okay, that leads perfectly into the next question. How are researchers planning to overcome this huge challenge? You can't just eliminate walls or stop the rain. How do you make these fragile terahertz signals actually usable in the real world?
This is where one of the most fascinating and potentially crucial enabling technologies for 6G comes into play. Reconfigurable intelligent surfaces, often abbreviated as RIS, sometimes also called intelligent reflecting surfaces, or IRS.
RIS, Reconfigurable Intelligence Surfaces. Okay, tell me about those. What are they?
So imagine essentially smart, electronically controllable surfaces. They're typically designed using special materials called metamaterials, engineered structures that can interact with electromagnetic waves in ways natural materials can't.
Okay, metamaterials, and you'd put these where?
You could potentially integrate them into the surfaces around us. Walls, ceilings, windows, billboards, maybe even painted onto objects. The key thing is that these surfaces aren't just passive reflectors. They can be controlled electronically, element by element, to manipulate impinging radio waves.
Manipulate them how? Like aim them?
Precisely. Instead of a T-Earth signal hitting a normal wall and being mostly absorbed or scattered randomly, an RIS can be programmed to reflect that signal intelligently. It can steer the reflected beam precisely in a desired direction, maybe focus it, or even split it.
Okay, hold on. So if the direct path between my device and the tiny 6G access point is blocked by, say, a pillar or another person, an RIS panel on the ceiling could catch the signal coming from the access point and deliberately redirect it, bend it around the obstacle straight to my device.
That's exactly the concept. They act like programmable, almost invisible mirrors or lenses for radio waves. They can create alternative, non-line-of-sight paths dynamically. By smartly controlling the reflections, they can effectively reshape the radio propagation environment itself to ensure a strong signal link is maintained, even for these very fragile T-Earth waves.
That's incredibly clever. Instead of trying to just blast the signal through obstacles, you make the environment itself help guide the signal where it needs to go.
It's a really fundamental shift in thinking about wireless network design, treating the physical environment not just as an obstacle course, but as an active, controllable part of the communication system. RIS are widely seen as critical for making T-Earth communication practical, especially indoors and in dense urban canyons.
Right. Okay, so we've got these incredible technologies being researched. Terabit speeds, microsecond latency, the network sensing things, AI woven into everything, these smart surfaces. It's all designed to enable applications that, frankly, still feel like science fiction today. What could 6G realistically mean for how we communicate and experience the world in the 2030s and beyond?
Well, with that kind of raw performance, the massive bandwidth and the near-zero latency combined applications that are currently clunky, low fidelity, or simply impossible become genuinely feasible. One of the most frequently cited examples is true high-fidelity, real-time holographic telepresence.
Holographic telepresence. So not just a video call, but like Princess Leia in Star Wars. A 3D person projected into your room?
That's the long-term vision, Maybe not full-on Star Wars initially, but imagine interacting with a photorealistic, life-size 3D representation of a person right there in your physical space. Seeing their subtle expressions, their body language, feeling a much stronger sense of presence. 6G could potentially provide the enormous data throughput and low latency needed to render and synchronize something like that in real time.
That would completely change remote collaboration, education, family interactions, pretty much everything.
Absolutely. And it's also seen as the key enabler for truly immersive and crucially believable augmented reality AR and virtual reality VR experiences, often grouped together now under the term XR or extended reality.
How so? Better VR headsets?
It's more fundamental than just the headset. The current limitations that often break the illusion of presence in VR, things like noticeable lag between your movement and the visual update, insufficient resolution or field of view, the headset needing to do all the heavy processing locally, many of those could be overcome by 6G. With near-zero latency and massive bandwidth, the really heavy computational rendering could potentially be offloaded to the network edge cloud. Your lightweight glasses just become displays. You could have incredibly detailed, high-resolution virtual objects seamlessly overlaid onto your view of the real world in AR, or fully immersive virtual worlds in VR, that respond instantly and realistically to your actions. The line between the digital overlay and physical reality could become incredibly thin, maybe even indistinguishable at times.
So XR experiences that feel completely natural and real, that definitely ties back to that core idea you mentioned earlier about fusing the digital and physical worlds.
Exactly. 6G is often positioned as the fundamental network infrastructure that's required to bring these kinds of hyper-realistic, context-aware, highly interactive spatial computing experiences out of the lab and into the mainstream.
Okay, another really fascinating application that hinges on that microsecond latency is this concept of the tactile internet. What exactly is that, and where might we actually see it used?
Right, the tactile internet. This builds directly on that ultra-low latency goal. It's essentially the idea of transmitting not just sight and sound over the network, but also the sense of touch haptic feedback, force feedback in real time.
Transmitting the sense of touch remotely, so you could like feel the texture or resistance of something happening far away.
Precisely. The ability to close the loop, not just seeing or hearing remotely, but physically interacting, feeling the remote environment through haptic interfaces.
Okay, where would that be useful?
The sources highlight its potential to absolutely revolutionize fields like advanced robotics and remote operations. Imagine, for instance, fleets of robots collaborating in a smart factory. With near-zero latency communication, they could achieve perfect real-time synchronization, almost like a single organism, sharing sensory data and coordinating actions instantly.
And the classic example, which always sounds amazing, is remote surgery, right?
Yes, remote robotic surgery is kind of the poster child for the tactile internet. Picture a specialist surgeon, maybe located hundreds or thousands of miles away. They're controlling highly precise robotic arms, performing a delicate operation. With 6G enabling the tactile internet, the surgeon wouldn't just be watching a video feed. They'd receive instantaneous haptic feedback through their control interface. They could literally feel the resistance of the tissue as the robot makes an incision, or the tension on a suture thread as they tie a knot, just as if their own hands were right there performing the procedure.
Wow, that's good. That could democratize access to expert surgical skills globally.
That's the hope. It could dramatically improve access to specialized medical expertise, especially in remote or underserved areas. But think beyond surgery, too. Remote repair of complex machinery, remote piloting of drones in hazardous environments with realistic feedback, even new forms of immersive entertainment where you can physically interact with the virtual world.
It really opens up a whole new dimension of remote interaction, adding that physical layer of touch and feedback that's completely missing from today's remote experiences.
It fundamentally expands the kinds of complex, skill-based tasks and interactions that could potentially be performed remotely. Yeah.
Now, the documents we look through, they also push into some territory that feels, well, even more speculative, definitely pushing the boundaries further out. What are brain-computer interfaces, BCIs, and this concept of global digital twins in the context of 6G?
Right, and the sources are usually careful to flag these as more futuristic long-term possibilities. They also explicitly acknowledge the significant ethical complexities and societal questions these raise, which need very careful consideration long before they become reality.
Understood. But exploring the potential edge cases. Let's start with brain-computer interfaces, BCIs.
Okay, so the thinking here is that 6G, with its combination of unprecedented bandwidth and that near-zero microsecond latency, might provide the necessary communication channel for high-fidelity, real-time interaction directly between the human brain and external devices or networks.
A direct brain link. Are we talking mind reading?
Not necessarily like science fiction mind reading. It's discussed more in terms of enabling much richer, higher bandwidth bidirectional data flow. Think about potential applications like allowing people with paralysis to control highly advanced prosthetic limbs with near-natural dexterity just by thinking. Or perhaps new forms of human-computer interaction that bypass traditional keyboards and screens. Maybe even deeply immersive virtual or augmented reality experiences that can adapt based on or even provide input directly to neural signals.
Okay, so less about reading thoughts, more about high bandwidth control and interaction pathways.
That seems to be the more grounded focus, yes. But even that is pushing the definition of connectivity into entirely new realms. It's definitely a frontier with immense potential upsides, but also, as you say, profound ethical questions that need navigating carefully.
Absolutely. Okay, what about the other concept? Global digital twins.
This idea builds very heavily on those concepts we discussed earlier, the sensing as a service capability and the pervasive intelligence embedded within the 6G network. The idea is that 6G could provide the underlying infrastructure needed to create, maintain, and continuously update highly detailed, comprehensive digital replicas, digital twins of vast, complex physical systems in real time.
Digital replicas of what kind of systems?
Potentially anything. It could be a digital twin of an entire factory, monitoring every machine and process, or a digital twin of a city's entire transportation network, or a complete energy grid, or a global supply chain.
So a dynamic, living digital copy mirroring the real thing.
Exactly. Some visions even extend to creating digital twins of large-scale environmental systems, or perhaps even highly detailed, personalized digital twins of individual human physiology for predictive health monitoring and treatment simulation. These twins wouldn't be static models. They'd be constantly fed real-world data, perhaps gathered by the 6G network's sensing capabilities and maintained and analyzed by the network's distributed AI.
And the purpose of having, say, a real-time digital twin of an entire city,
Yeah.
what would you actually do with it?
You could use it for incredibly powerful simulations, predictions, and optimizations. Imagine testing the impact of major urban planning changes virtually before digging a single hole in the ground. Accurately predicting traffic flow patterns minutes or hours in advance to proactively manage congestion. Optimizing the city's energy distribution grid in real time based on actual demand. Simulating the impact of extreme weather events to improve emergency response. Or even predicting exactly when a specific bridge component might need maintenance based on real-world stress data.
Okay, so it's like having a dynamic, executable simulation layer of the real world, constantly updated, allowing you to test what-if scenarios and optimize complex systems on an unprecedented scale, made possible by 6G's ability to gather, transmit, and process that vast amount of real-world data.
That's the core idea. It's fascinating, maybe slightly overwhelming to contemplate the scale, but it really highlights the ultimate ambition, creating this functional dynamic replica of reality, or aspects of it, to help us better understand, manage, and interact with the complex physical world around us.
It's definitely clear this isn't just some academic thought experiment. There's a serious global effort, almost a race, it feels like, to develop 6G technology first. What's the status of that global research race right now, here in mid-2025, and where does Canada fit into the picture?
You're right, the sources definitely emphasize that the journey towards 6G isn't happening in isolation. It's a long-term global endeavor, really, a marathon, not a sprint, and it's already well underway. Major economic blocs, major nations, are actively investing significant resources and competing for leadership in defining and developing this next generation of wireless technology.
Who are the main players we're seeing making big pushes in this global race?
Well, you see substantial coordinated national efforts coming out of China, the United States, the European Union as a bloc, South Korea, Japan. Several others are also very active. They've all launched large-scale research programs, often involving close collaboration between universities, industry players, and government funding agencies.
And why the race? What's the perceived advantage of leading in 6G?
It's widely recognized that setting the standards and owning the core intellectual property for the next generation of global connectivity could provide a significant economic and strategic advantage for decades to come, just as leadership in previous generations did.
Okay, so where does Canada stand in all this? Are we participating or mostly watching from the sidelines?
According to the documents we reviewed, Canada is definitely positioned as an active participant in this global research landscape. We're not necessarily trying to compete head-to-head on the scale of, say, the US or China, but Canadian researchers are making significant contributions to the foundational science that will underpin 6G.
Like in what areas specifically?
The sources often point to Canada's existing strengths. For instance, our national quantum strategy aligns well with exploring those quantum-resistant security mechanisms we talked about. And perhaps even more relevantly, Canada has world-renowned AI research institutes and a strong talent pool in artificial intelligence, which is absolutely crucial for developing that AI-native network architecture that's so central to the 6G vision.
So Canada is contributing key pieces of the puzzle, leveraging our strengths in quantum and AI.
Just exactly. The strategic goal seems to be ensuring that Canada isn't just a late adopter or a consumer of 6G technology developed elsewhere, but rather that we actively contribute to its development, help influence the global standards and ethical discussions around it, and ultimately position ourselves to benefit from the economic opportunities and societal applications that 6G will create.
Right. Okay, so as we kind of wrap up our deep dive into these early visions for 6G, it's abundantly clear the goals are incredibly ambitious. We're talking about pushing the boundaries of physics, engineering, computer science. What do the sources identify as the absolute biggest hurdles that still need to be overcome? And stepping back, what's that ultimate driving vision they keep coming back to?
Well, the sources are generally quite candid about the scale of the challenges ahead. They don't shy away from that. On the pure hardware and physics side, developing cost-effective, energy-efficient, and mass-manufacturable components, transistors, antennas, amplifiers that can reliably generate, process, and detect those extremely finicky terahertz signals at scale. That remains a major material science and engineering problem that isn't fully solved yet.
Getting terabytes out of the lab and into billions of devices affordably and reliably.
Precisely. And then there's the complexity of managing that AI native network we discussed.
Right, the network that runs itself.
Designing, implementing, and trusting the incredibly complex AI algorithms and distributed architectures needed to autonomously manage a network of this potential scale, speed, and dynamic complexity. That's a monumental computational and algorithmic challenge in itself. How do you ensure it's robust, fair, secure, and performs as intended under all possible conditions?
Another grand challenge for sure. And then layered on top of the technical hurdles are the human and societal elements, right?
Absolutely critical. The profound security vulnerabilities, the privacy implications of pervasive sensing, the ethical dilemmas raised by potential applications like BCIs or highly detailed digital twins. These must be addressed proactively, transparently, and built into the design philosophy from the very beginning. They can't be afterthoughts tacked on at the end. Building and maintaining public trust in a system this powerful and pervasive will be paramount.
So, significant technical mountains, huge computational problems, and deep ethical considerations to navigate. Despite all of that, what's the core motivating vision that seems to drive all this intense research and investment? What's the ultimate why?
I think the ultimate vision, the thread that runs through all these documents, goes right back to that initial concept we started with.
Yeah.
6G is envisioned as being fundamentally more than just a faster communication network. It aspires to be a foundational distributed platform, a pervasive, intelligent technological fabric that seamlessly fuses our digital experiences with our physical reality. It's about creating a future where the network isn't just something we use, but is an active partner in sensing, understanding, predicting, and maybe even helping shape our environment and our interactions within it.
A vision that really aims to fundamentally change our relationship with technology and the world around us, pushing towards a future that feels truly integrated, maybe even symbiotic.
That's a good way to put it, yes. And while it's important to remember we're still in the early research and development phases, widespread deployment is likely still a decade away, probably starting around the 2030s. The ambitious goals and the revolutionary concepts being outlined in these documents today are already steering the direction of research and pushing the boundaries of what scientists and engineers believe might be possible tomorrow.
It really does promise a future where those lines between the physical, the digital, and maybe even the human biological world begin to blur in ways that honestly we're probably only just beginning to comprehend. What possibilities does that future spark in your imagination?
It's certainly a powerful question to ponder as we look ahead.
Indeed it is. Well, thank you so much for walking us through that complex and fascinating landscape.
It was my pleasure. A lot to think about.
Definitely. And thank you, our listeners, for joining us on this deep dive into the emerging world of 6G. We hope you found this exploration as thought-provoking and maybe even a little mind-bending as we did.
Right.
If you want to keep exploring the cutting edge of technology, AI, and where it's all heading, please make sure you're subscribed to our channel, Tech, AI, and Beyond. We'll be back soon with another deep dive.